Okay guys, welcome. We're going to look at some of the effects of forces now. And so you have this packet of notes that you can go through, as well as the handouts that are associated with it. So the two questions we want to answer to start off with: how do forces affect the motion of an object? What's the difference between contact and field forces? And how is a free body diagram constructed? So let's get going on this information. So to start off with, a force is simply a push or pull that's exerted on another object, and that forces creates a change in velocity. So it's important to know that forces don't keep things moving. Forces make them move faster, slower, or change their direction. So forces can start or stop motion. Forces can change the direction of a motion. All right, so since velocity is defined as speed and direction, then a force can change the speed or change the direction. That means forces make things accelerate. Accelerate occurs three ways: speed up, slow down, or change direction. So it's important to remember that when an object is traveling the same speed, the forces are balanced on it and there's no net force making it go faster. Force, the SI unit for a force is a Newton, and a Newton is simply defined as the amount of force needed to accelerate 1 kilogram 1 meter per second squared. So if you have a mass that's 1 kilogram and it's getting faster 1 meter per second every second, then that is 1 Newton of force applying that. Okay? So the weight of an object is a measure of the magnitude of gravitational field acting on an object that has a mass. So one of the number one forces that are out there is weight. Okay? So a force makes something move faster, slower, or changes its direction. The SI unit of a force is a Newton. A Newton is defined as 1 kilogram moving 1 meter per second faster every second. And one of the most common forces that we can't get away from is weight. There are two basic types of forces, either contact or field forces. And of course, a contact force is when two objects come into contact with each other. And then a field force, there's two main categories of those: gravitational forces or electromagnetic forces. So you don't have to be in contact with Earth for gravity to take effect on you. Magnets, you don't have to be touching the magnet for one magnet to pull on another magnet. These are electromagnetic forces and gravitational forces. They are examples of field forces. The thing I want you to know about field forces is the further you get away, the less the field force has effect. So the further you get away from a magnet, the less the magnet pulls on you. This is the same thing with gravity. The further you get away from Earth, the less Earth pulls on you. So two main types of forces: contact forces and field forces. When we do forces, we label them and draw these diagrams called free body diagrams. So the change in motion due to a force depends on two things. It depends on the magnitude and the direction. So since it has a magnitude and direction, that means that force is a vector. And so if we have vectors, we can use force diagrams to draw and model the force that's acting on that system. In a force diagram, the tail of the vector is attached to the object. So for example, if we draw this would be an incorrect diagram. We would say a force pushes the box. We might draw this. This is incorrect. The correct drawing would be a force pushes the box, because the tail of the vector is attached to the object. So we do see this diagram sometimes, but it's an incorrect vector diagram. This is the more correct free body diagram. You must disregard the shape and the size of the object and assume that the force acts at a single point. So we're just choosing this point right there. We're not worried about how the shape of the box is or the shape of the object. If we were to study the forces on a hammer or a baseball bat, we would just pick one dot to represent that object. We wouldn't worry about how long it is or the individual shapes of it. Free body diagrams and force diagrams. The tail of the vector always connected to the object. Okay? When we're drawing a free body diagram, which helps us to analyze all the forces on a system, we draw just a basic shape to get it started with, and we draw and label the vectors representing all external forces. So we draw forces that are acting on the object, not what the object is doing. So if we take, for example, say we have a car, and that car is pulling some object. Okay, so it's attached to this slide or whatever, this object over here. So if we draw a free body diagram of this box, the car pulls on the box. Does the box pull on the car as well? And the answer to that is yes. But if I'm only drawing a diagram representing the box, I do not draw the box pulls on the car. That is a force, but it is not drawn on the box. Okay, so we don't draw that one on the box. So what other force is acting on that box? Well, we know the car's pulling on it. There's another force acting on it that we diagnosed earlier, and that force is the weight. We can include that. And you probably guessed there's another force out there acting on that box that's keeping it from moving, and that force is our friction. So that's the basics of a free body diagram, getting started with. And so for a free body diagram, you need the tail connected to the object. Just use a dot or something like that, or maybe a small box to represent that object. And only draw the external forces. Only draw the forces that are acting on the object, not the forces that the object exerts. So the box exerts forces on the car, the box exerts forces here and there, but we don't draw those. We only draw what's acting on the box. So if we go back up to answer our questions, how do forces affect the motion of an object? We saw that. What's the difference between contact and field forces? And then finally, how do you draw a free body diagram? So you can go back and look at the notes and answer those questions. Let's take a minute to look at an example question. So practice problem A, you'll see that in your assignment. You can work on those. I'm going to go ahead and move down here to number 5. Let's draw our first free body diagram from this information. Then I'll allow you to work the rest of it. A physics book is at rest on a desk. Gravitational force pulls down on the book. So there's one force. So to start off with these free body diagrams, I'm going to give you the forces. You just draw the forces that I give you. You don't worry about any other forces that you might think exist. There could be others, but just draw the ones that I'm asking you to draw. Gravity pulls down the box. The desk exerts an upward force on the book. Equal in magnitude. So if it's equal in magnitude, we're going to draw those vectors the same length and draw the free body diagram of the book. Okay? So you can draw a book if you'd like. You can try to draw some book. But we can basically just draw a point, and that point is the book. We have two forces acting on it. Gravitational force pulls down. We just draw an arrow down, and we call it weight, or force of gravity on the book. There's another force that is equal in magnitude, so I'm going to draw it that same length, and it is going upward. So we just simply draw force upward, okay? You can label that force several different ways. You can call it the force upward. You can call it the force of the table on the book. A couple different ways to label it. You'll see as we start working with this, we'll start labeling these forces with little names and little letters underneath it. So what I'd like you to do is try 6 and 7 and look through the notes so you can see, for example, when you get down here to the bottom of this worksheet, we have this one about the boy on the cliff. And then I provide you an answer for that. So give those a try. Free body diagrams and the basics of forces.